Okay, I'm going to go through 17.2, which is infrared spectroscopy. This also includes some information on global warming, which could be tested in the exam. So, and that's because infrared is important in the heat that the Earth has. Okay, so let's get started. As you can see behind me, I've got the criteria from the spec. So we'll get started with this now. So you should be able to see the screen now. So first off, infrared spectroscopy is very important in identifying organic compounds. So you need to be able to recognize all the different functional groups that you can. And I'm going to put a slide up in a second, which will show you the most important ones that we need for A-level chemistry. And then we need to sort of also understand the idea of the electromagnetic spectrum. There is obviously infamous electromagnetic spectrum song on YouTube, which you can find, which will help you to go through it. But basically, this picture here shows the electromagnetic spectrum, shows that we can obviously with our eyes recognize visible light, which is actually reasonably high energy, enough energy for it to cause us to innovate certain earth pathways in our brain so we can see. But you can see that there's various areas of the spectrum. Infrared is below visible light. Now by low, I mean, you know, it's to the right on this diagram, because it's increasing wavelengths but lower energy. So infrared is lower energy than visible light, but higher energy than radio waves. Microwave is sort of coming in this region here-ish. Okay, and that is where all our mobile phone technologies sort of originate, and Wi-Fi, etc. And above visible light, obviously we've got ultraviolet and X-rays and gamma rays. Okay, and we talked about ultraviolet when we considered topic 15. Okay, so let's move on and let's have a look at those functional groups. So you have come across alkanes, alkenes, alkynes we've sort of touched on, alcohols we've done. We haven't done ethers, and ether basically is where you've got two carbon chains linked by an oxygen. They don't actually play a major part in the organic chemistry that we test, but just note they're around. Epoxides definitely don't come into the spec, but you can see it's two carbons with an oxygen, you know, sort of making a triangular sort of cyclo group. Haloalkanes we have done. Aldehydes we have considered. We'll do more about them in year 2, and ketones and carboxylic acids. We'll also come on to acid anhydrides. We've mentioned esters, and we've smelt some. Well, we will smell some esters, and we make aspirin. We'll do that. Amides will come across. Acid chlorides or acyl halides will come across. Amines, nitriles. Nitriles we'll already sort of come across because we can add the CN as a nucleophile to something that has got a susceptible to nucleophilic attack, like a haloalkane. We won't do imines. Isocyanate we won't do. Azo compounds we don't do, but they are done in the other chemistry spec. Thiols we won't do, but some you do in biology may recognise that as part of protein structures. Arenes we will do. Okay, so those are our most common functional groups in organic chemistry. So we have a technique where we can recognise them, and that is infrared spectroscopy, infrared IR for short. And they're the pages in the book. So here are our ideas. We've got to understand that infrared actually affects covalent bonds, where they absorb energy. It doesn't break them. It's not enough energy to break them, unlike UV, which is enough to break them. Remember that UV can break a chlorine-chlorine bond homolytically to make free radicals. Infrared is not enough energy to do that, but it can make them vibrate. Okay, and we can think of, you know, infrared is really important for use in a wide variety of activities. It's absorbed by CO bonds, OH bonds, CH bonds, in carbon dioxide, H2O and methane. And this is where the global warming comes in, because infrared is absorbed by these bonds. We can obviously, we will get onto this, is very important, and we will need to try and identify compounds. There is the idea of this fingerprint region, or part of the spectrum, which is can be used with computer technology to actually identify compounds completely, if they're in the database. And we can determine the structure of compounds from it. Right, now in your booklet there are some keywords, but I think we need to add these ones to it. So the fingerprint region, area below 1500, that gives a characteristic pattern for different compounds. Wave number, okay, which is used in a lot of chemistry. Basically, it's a simplified way of considering wavelength of the waves. So we measure it in centimeters to the -1. It is the inverse of the wavelength. And it also is related to frequency. So if you have a high wavelength, you'll have a low frequency and a lower energy. So the longer wavelengths have got lower energy and lower frequency. Higher frequency and higher energy have got smaller wavelengths. Wave number is the inverse of wavelength. So wave number increases as frequency increases. Okay. And there's that diagram of the electromagnetic spectrum. Okay, so if you feel like it, you can watch the electromagnetic spectrum song just a really quick. So what's happening? Okay, we've got these covalent bonds. They are bendy. Okay, in a molecule, they're not held rigidly together. So we talk, using the monomod kits, it looks as though the bonds are stuck together with these very rigid things. They're not. Okay, they move as if attached by a spring. Remember, the electrons are always moving. Okay, and Heisenberg's uncertainty principle is that you can either know where the electrons are going or where they are, but you can't understand both at the same time because they're always constantly in motion. Okay, if you want to find more, there is a link on the PowerPoint, which obviously you can find this PowerPoint on Moodle. Yeah, there we go. Okay. So different covalent bonds got different strengths. Obviously, we know that double bonds have got a higher energy, but not double, higher energy than single bonds. Etc. Okay, and what we've got is we've got different atoms with different masses at the ends of springs. In effect, I mean, by considering springs, we're sort of idealizing the bonds a bit of an ideal situation. Okay, but we have these atoms with bonds, and they are connected by bonds, and the bonds can vibrate, and the frequency is going to be related to what energy they absorb. And they'll absorb this electromagnetic radiation and get different types of vibrations are possible. Right. Okay. So, yeah, what we're talking about is that the energy is absorbed by these bonds. Okay. And a classic example is my first car was an old Mark I Ford Fiesta. It was a bit souped up, but as I hit 69 miles an hour, what happened was my dashboard started to vibrate at almost exactly 69 miles an hour. Okay. And so if I went faster, okay, say like 75, then it stopped vibrating. But at 69, I slowed down and it gets to 69 and it would vibrate. Really loud. That's called like a resonant frequency. It's the frequency of the vibration of the car on the road, the speed of the wheels turning, all that sort of stuff. And that vibrational frequency was perfect, or was what we call the resonant frequency for that. Obviously, I'm not advocating driving faster than 70 miles an hour on the motorways. Let's share my screen again. Okay. So bonds are the same. They can absorb energy and they have their special resonant frequencies. And what happens is that they get these frequencies, they absorb these frequencies, and that heightens or increases the chances of those bonds stretching and bending. Okay, so I can, let's just do a demo of that. So, right, so we have got stretching. So here's my arms, here's my body. If you imagine my middle of me is an oxygen atom, there's my hands are the hydrogen atoms. So stretching is that. Okay, so I'm taking some infrared energy and I'm increasing the rate at which I do that. And it's specific for the specific energy of a certain bond. So perhaps this is oxygen, this is hydrogen. Okay, an OH bond has got a certain energy, 400 and something kilojoules. Okay, and it absorbs that energy. Okay, so that's stretching. I can also have bending. Okay, so bending would be like this. Okay, and I could also have asymmetric stretching, which would be like this. Okay, so you get the idea, and hopefully I've got some nice animations which hopefully will show up on the next slide. So let's have a look. Okay, so we've got symmetric stretch, bending, asymmetric stretch, which I just demonstrated. So symmetric stretching, okay, there's the oxygen and the hydrogen. Okay, that's water molecule, that would be doing that. Okay, asymmetric stretching, okay, and bending, yeah. Okay, so that's all ways that the bonds can absorb the energy and react. Okay, so a bond, you know, and I talked about this idea of the resonance frequency. Frequency values are very large, okay, so they're quite hard to use to plot stuff. That's why in chemistry we move to the wave number. So in infrared, the frequencies of infrared go from about 3 times 10 to the 11 to 4 times 10 to the 14 hertz. Or if we use prefixes to help us to deal with those large numbers, 300 gigahertz to 400 terahertz. Yeah, T is for tera, G is for giga. Hertz means cycles per second, i.e. one wave per second. Okay, so that's 300 times 10 to the 300 times 10 to the 9 hertz is 300 gigahertz, or 3 times 10 to the 11. Okay, so we use wave number. It's proportional to frequency. It's measured in centimeters to -1, and that means our numbers are much more easy to deal with. We have, you know, the infrared range of what we measure is from 200 to 4,000 centimeters to the -1. You can obviously look that up on various online systems. Okay, so the greenhouse effect then. Okay, so we're talking about this energy being absorbed. You know, hopefully you can think of this. You could stop the video now if you wanted to, and then carry on. Okay, so greenhouse effect and global warming. What is the difference? Okay, greenhouse effect and global are not the same thing. Okay, so the greenhouse effect is increase in concentration of greenhouse gases increases the magnitude of the greenhouse effect. This enhanced greenhouse effect, and you know, the vast number of scientists now agree that human anthropomorphic emission of carbon dioxide has contributed to an enhanced greenhouse effect. So the greenhouse effect is the effect, and this result in global warming is a rise in the average temperature of the surface of the Earth. So global warming is a rise in the average temperature. The greenhouse effect is the increase in magnitude of the greenhouse effect, in other words, trapping heat and then re-releasing it. So Earth gets its energy from the sun, and that causes the atmosphere. The Earth's surface is about 35 degrees warmer than it would be without an atmosphere, so it's important we have the greenhouse effect. And we can also look to places like Venus, and you can see Venus is an example of a planet where the greenhouse effect has gone way too far. Okay, and Mars is an example of where the atmosphere's got so thin that there's very little greenhouse effect. Okay, this is for our survival. So a lot of the light passes from the sun and it doesn't get reflected back because it's absorbed by the planet, but also greenhouse. So some of it gets reflected from the ground and should go back out to space, but it doesn't, because greenhouse gases in the atmosphere, they absorb long wave radiation, infrared. Okay, so the gases in the atmosphere absorb the infrared, but they don't absorb the shorter wave light. So that's the higher energy light. So thus we store energy in the atmosphere. Okay, so here we have an example. The sun's light comes in. Some of the radiation, which is UV or whatever else, will get reflected and go straight out into the atmosphere. But it's the atmosphere that traps the infrared. Okay, so here, this light here is this infrared, which is being reflected back. So the Earth is warming up, so the surface is warming up. It then releases that energy back to go out towards space, but the gases absorb it, and then they will re-release it to keep it warm. Key points. Page 250 in textbook, summarize them. Okay, so stop the video, go into textbook, summarize them, and then come back. Okay, welcome back. So here are the key points that you should have found from your textbook. Most radiation passes through the atmosphere to the Earth's surface where it's absorbed. It is re-emitted from the Earth's surface in the form of longer infrared wavelengths. So it's released, but it is changed in its frequency. Its frequency gets lower, so we have longer wave. Yeah, so it's higher wavelength, lower frequency. The greenhouse gases absorb this longer infrared radiation because it's got the right frequency, the resonant frequency of the bonds of the gases in the atmosphere. Eventually, those vibrating bonds then re-emit the energy as radiation, which will increase the atmospheric temperature. So the atmosphere, okay, so we know hopefully you know that the Earth is pretty much about 21% oxygen, 79%-ish, 78% nitrogen, plus some other gases. Okay, so there we go, there's the other gases. And carbon dioxide is 0.035%, or at least it was earlier in the last century. Okay, at the turn of the 20th century, it was about 0.03. I think now they're reckoning it's higher than 0.035. So, greenhouse gases. Water vapor is a pretty strong greenhouse gas. Carbon dioxide and trace gases as well. Ozone, okay, at the wrong level. We know that ozone at the right level is okay. Methane is a very bad greenhouse gas. Nitrous oxides that we produce from burning fossil fuels, and CFCs. So, although CFCs have now been banned, they did contribute to the greenhouse gas effect, and we still have got some CFCs being used until everything has been phased out. But remember, this is a different problem to what CFCs cause with the ozone layer. Okay, so greenhouse gases. So you can see the bonds that absorb energy in your textbook, and it's also on the data sheet, which I'll show you in a bit. So which greenhouse gas contain these bonds? So CO2 contains CO, okay, which is will definitely absorb infrared radiation. Water contains OH bonds, that will absorb it. Methane contains CH bonds, also absorbs infrared. CFCs contain CF bonds. Okay, so what vibrations could CO2 undergo? Well, that's those ones I demonstrated earlier. It also undergoes bending and stretching. Okay, eventually the molecule will re-emit the energy in the form of radiation. Okay, did my car dashboard get hot? Well, it did if it was in the sun, but it, obviously it resonated with the right frequency. So there's the sort of bending and stretching that carbon dioxide can undergo, whether it looks like it's bending there. Okay, so CO2 levels. We can actually, or we have satellites that monitor it, and devices in the atmosphere that monitor it. So we have an infrared atmospheric sounding interferometer used to measure carbon monoxide. Okay, so this is carbon monoxide and CO2 in the atmosphere can be measured using these devices. And we need to look at the levels in parts per million. And if you look at those pictures, you can see that a lot of the CO2 is on the eastern seaboard of the United States and the western seaboard, quite a bit around Europe, and especially sort of like across the Urals in Russia, quite a lot around the middle of Africa. Okay, carbon monoxide, a lot around the Beijing area, and I think that's Korea there. Okay, so the levels are higher where we are more industrialized. So what we're doing about it, well, hopefully, and we are trying to work towards it. And obviously last year we had the delayed COP27 in Glasgow, should have been in November 2020, but of course we had the pandemic. And during the pandemic, of course, lots of people stopped flying, and flying reduced, and the air did become cleaner. But it's already got back to where it was before. So you can find out about climate change here. Okay, so what are we going to have to do? Well, we're going to have to stop using renewable fossil fuels and just use renewable sources of energy. Okay, potentially we could do carbon capture and storage. And people are working on that. Use less energy, waste less energy. So if we insulate all our homes, would be a very good idea. It'd be interesting. It would be a good idea for the government to spend money on insulating all our homes, so we don't have to use so much energy. Perhaps all new builds should have solar panels. Okay, more efficient cars like electric cars. Okay, and processors. Although new electric cars are not going to be carbon negative until about 40,000 miles, but there is the production cost of the car and the transport costs in the first place. But after a certain point in time, electric cars are carbon neutral. Are we doing enough? Well, yeah, you decide. Okay, so how can we measure the energy absorbed in these bonds? We use a spectrometer, an infrared spectrometer. Now, this is the first example of where we're using electromagnetic spectrum to measure compounds. Okay, previously used mass spec, which actually really isn't spectroscopy as such, although we call it a mass spectrometer. This is proper spectroscopy where we use the spectrum of light to look at stuff. So here is an infrared spectrometer, or a diagrammatic representation. Beam of infrared, so we have an infrared light source, so that's going to be a hot lamp because the heat that it's generating is going to be coming out as infrared. We have a filter to make sure we get the right wavelengths of the wavelength there, get the right wavelengths through. Light is not going in all it does go in all directions. We use a slit to make sure we get it going straight through our sample. So we have a sample cell. Okay, and we put our organic substance in here and we pass infrared through, and the organic substance, the bonds in it, will either absorb the energy or not absorb the energy. The energy that's not absorbed, i.e. transmitted, will go through. Okay, so we get that. The bonds absorb some. And we can identify it. And basically, it's just a computer that plots a graph of percentage transmittance against wave number. So, yep, it's a box, okay, and you put your substance in, and if it's a modern one, you'll have computers connected, and it will probably help you to identify it, okay? But you need to be able to identify the basic principles of infrared by looking at some spectra. So there are many different vibrations that can happen, because obviously if you've got a big molecule, it's going to have lots of different bonds. So what's going to affect the factor? The bond strength, the mass of the atoms, and what will affect the peaks. Okay, the size of the peak will depend on percentage absorbance, how much of the radiation is absorbed as it passes through, or percentage transmitted, how much passes through, how much is absorbed. Yeah. Okay, so you can see the different, you can look at the difference between transmission and absorption. Now, we will now see a spectrum. It looks slightly tricky, but it's not so difficult when we realize that most of it is the fingerprint region, which we don't need to worry about, okay? We call it absorbance, and we call this a peak, but in fact, actually it's a trough. Yeah, so you can see it's going down, but we call this a peak. So we've got a very large peak here between 1600 and 1800. That is a characteristic of certain organic compounds. We've got this peak here, which is characteristic of, well, what is going to be present in pretty much all organic compounds, CH. That's the CH peak there. And then we've got this region called the fingerprint region. So let's so we've got on the vertical axis, we've got the absorbance, how much is absorbed. Okay, so we're actually measuring transmittance, and that's why the peaks are reversed. Yeah, so we're having here about 50% absorbed. Here is about 90% absorbed, because we're about 90% absorbed there, 10% transmitted. So only 10% of the light gets through here. Most of it is absorbed. 50% of the light light of this wavelength or frequency, wave number, gets through. Okay, so we have that. Okay, and the horizontal axis obviously is the wave number or frequency. Okay, now we said wave number because that gives us nice numbers without having like loads of exponential, not exponentials, but powers of 10 in it. Okay, so we go from 4000 to 600 in our spectrum, which is the infrared region that we're looking at. Okay, so we have this region here. Now that looks pretty tricky. It's the fingerprint region, 400 to about 1500. Okay, it's important because it's called the fingerprint because you can identify a compound from it if you have patterns that match that. So we use a database and we can quickly identify compounds. Now, it used to be that you couldn't really use this to identify specific compounds because we didn't have the computing power to do that. Pattern matching is a classic use of computer power. Computers aren't intelligent, but they can look at patterns and find patterns very quickly. So we could use that to do that. Okay, so looking at functional groups. So look at your data sheet. Okay, so here is a data sheet. It's on the inside page. Okay, you've got some key data here, and then up here, if I can see that, oh, it's going to disappear. Okay, so there it is here. This is a list of bonds and where they appear, and it also describes them as strong peaks or broad peaks or weak peaks. Okay, so it tells you what frequencies or which wave numbers that they absorb. If there are no peaks in the region that's listed on the datasheet, then it's, oh, hang on, let's put the screen back on. Okay, so it's a list of the bonds with characteristic peaks. Okay, if there are no peaks in that region, the bond is not present. Okay, so classic number one. There are only about 4 to 5 things to remember, but the first one is this. This is a carbonyl compound. Okay, it's got a little CH peak. Okay, so there can't be that many CH bonds in it, but it has got CH bonds in it. That's that peak there. That's not highlighted when we go through this PowerPoint, but that's CH. This is the carbonyl peak. It's between 1600 and 1800. So carbonyl is CO. Its absorption range, and this would be the same for carbon dioxide. Okay, strong absorption there. Okay. And it's due to the carbon-oxygen bond stretching. Okay, the next classic one, okay, is this. This is an OH peak, okay? You can see the CH, this is this peak here, so you got this second peak here, and I'm going to keep pointing out this one, this is CH, okay, and this is an OH. Now, in fact, this is cyclohexanol, and the fingerprint region will help us to identify it's cyclohexanol, but the key thing is we can identify it as being an alcohol because of this peak here. Okay, that peak is OH. Hydroxy. Its absorption is a broad absorption between 3,200 and 3,600. Now, broad, okay, means it's quite wide, okay, and it's quite strong because it's, it goes, the peak is, well, the peak, or I say it's called a peak, but it's actually a trough. The trough is quite deep, so it's a big peak. Okay, and there we go. Okay, and it's got OH stretching, and also CO. Well, we're going to have CO here, aren't we? So carbon here, oxygen here. CO stretching is going to be in this region here, but that's the fingerprint region, so we don't need to worry about it too much. Okay, so we've got the OH. So we've done carbonyl, we've done OH, and also we've got this side thing of being the CH here. Okay, next spectrum. This is a carboxylic acid. Now, carboxylic acid is going to have CO. There's that one. It's going to have OH. But what's happened here? The CH is not a separate peak, unlike here where CH is a separate peak. So here is our OH, and the CH has been sort of subsumed. We would call this a very broad peak. Okay, so you've got both CO and OH, but they're next to each other because they're in the carboxylic acid group. So we would label this as a very broad peak. Okay, so you might want to record that when you're answering the question. 2,500 to 3,300-ish. Okay, and it is OH bond stretching, but it's in an acid. Okay, so strong absorption here, which is the acid. Okay, so let's have a look at this. So what have we got? That is going to be OH stretch, so that would be an alcohol. It's called a broad absorption, 3,200 to 3,600. That is carbonyl stretch, okay? Strong absorption, 1630 to 1820, CO bond. Could be an aldehyde, ketone, or an ester. Can't be an acid, okay, because we don't have this peak. Notice we still have the CH peak. Remember this CH peak, that's another one to remember. Okay, right, this one, we have got OH stretch and CO stretch, but we've got this very broad peak, so that is an acid. Okay, strong absorption there. Okay, 2,500 to 3,300, carboxylic acid. Okay, right. Now, if you had doing questions from the old spec, then wave numbers have changed. Okay, always use the ones on the data sheet. And the new data sheet. So some of the mark schemes may give a slightly different range, but you use the ones, the range from here. Okay, right, identifying functional groups. Okay, what kind of compound is that? Well, yeah, you can think about that. Pause the video and think. Okay, well, we've got this very broad between sort of 2.5 to 3.8. Yeah, and we've got the CO. It's an acid. Yeah, it's carboxylic acid. What if it looked like this? Okay, now this is an interesting one. This is just to check your understanding. I've got carbonyl, but I've got OH and CH. The CH peak is visible this time. It's a broad peak, not a very broad peak. Okay, this is an aldehyde or ketone and an alcohol. It's not an acid. Okay, so the OH is not right next to the CO. Okay, so if we're going to answer these questions, we need to write down the wave numbers for the absorptions and peaks that we can see. We can write down what bond that is characteristic with by using the data sheet. You can then make some conclusions. Example, the spectrum has a strong absorption, It's got a broad peak, OH, it's got alcohol with it, and so this is the peak that you just saw. Okay, it's got a compound, must be an alcohol with a ketone or aldehyde group within the molecule, but not next to each other. So, why do we use it? How unsaturated or saturated a polymer is. Perfume manufacture, we can identify the chemicals. Monitoring air pollution, okay, new and unknown compounds, we can try and find, analyze them. We can analyze drugs. Now this is a classic because this is where breathalyzers come in. We can compare the infrared spectrum, an unknown sample with a known one. So for instance, we could look at ethanol, okay, and that's how breathalyzers work. Okay, you would give somebody a breathalyzer, it would detect organic molecules in their breath, and we'd get the characteristic OH peak, and we'd have a characteristic fingerprint region, which would be the same as ethanol's. Okay. So putting it all together, we use a wide range of sources. We can use elemental analysis. You should know about that. That's where we try and work out the percentage of carbon, hydrogen, oxygen in something. That will give us an empirical formula. We use mass spec, which we have done. Mass spec will give us a molecular formula that allows, because we know the total mass, if the mass is the same as the empirical formula is the molecular formula. If it isn't, it's going to be an integer difference. We look at fragmentation patterns, okay, and we can now use infrared spectroscopy, which will give us our functional groups. And we can also use a database of spectra, but that we wouldn't use that in the course at the moment. That'd be if you were working with infrared spectroscopy later on. As an example, it's in your textbook. We'll go through it together. Okay, so get your textbook ready at 256. Okay, so let's have a look at it. Right, so the molecular formula, we've got a C, H, and O in it. We've got our percentages. We divide them by the masses of those elements, and we can work out the ratio. We get a ratio of 4.65 to 7 to 2.3, okay, which we would, or 2 to 3 to 1, C2H3. The molecular formula, however, is C4H6O2, okay, because we've got the mass spec. The mass spec gives us some peaks, so we've got C3H5 peak and we've got a COO peak because COOH is 45, has a mass of 45. Okay, so we have got a peak indicating presence of carbonyl, and we've got a broad peak indicating the presence of OH. In a carboxylic acid, it's a very broad peak. So our correct structure is this. We've got 1, 2, 3, 4 carbons. We've got 1, 3, 4, 5, and 6 hydrogens, which is consistent with our composition analysis. And we've got the oxygens written out like that. Okay, so that is what we've got there. Okay, so therefore, finally, okay, I'm finished, and you should have a go at those things before you get to your lesson. Okay, thank you very much.
What are you doing that for, Nick?